So today, 13th of December, we are going to do chapter 9, okay, which is going to talk about virtual memory, all right? So before we go into detail, let me just give you a bit of highlights. What are we going to do in this chapter? All right, we are going to do demand paging, demand segmentation. We're going to understand what is virtual memory, and then we are also going to look at page replacement technique, whereby we are going to look a bit more detail on paging and how the operating system handles if there is no frame available or there is no files available. What does it do? How does it do it? And there's a few algorithms that we need to understand, and we are going to learn. Okay, so let's start. So we are going to look at virtual memory today. We are going to look about demand paging, page replacement technique, allocation of frames, and about thrashing. And we are also going to highlight about demand segmentation. We are first going to describe later on in the slide what is virtual memory first, before we can start going into demand paging, demand segmentation, page replacement algorithms, and other forms of algorithms. And we are also going to look at allocation of page frames. So basically, why do we need paging and demand segmentation, or demand paging and demand segmentation? Is simply because codes or programs that are needed to be executed needs to be in the memory, but not entire program is used. Okay, so when the program or process needs to be executed by the CPU, not the entire codes need to be inside the memory for the CPU to run. Okay, so you have to understand, in any process, okay, any process, any process, the programs will be brought into the memory first, your RAM, and then later put inside the CPU to be executed. Okay, when the file is needed to be executed, or if the CPU needs to execute certain codes, certain files, it would first look at the RAM to locate if the files or the codes are there. If not, it will locate back at your hard disk to see if the codes are still there. All right. In the CPU, okay, in the CPU, there are also two more memories, which are the registers and the cache. Even inside this memory, which is the cache memory and the registers, there are certain files. However, if the files are not located in this location, the CPU will start looking, or it will send a signal to the memory to locate those files. And if the files are not inside the memory, it will send another signal to the hard disk to locate those files and bring back those files inside the memory for it to be executed. Okay, so basically, the CPU is able to execute partially loaded program. It's always loading partially loaded program, because not all codes, not all files are needed to execute a particular program. All right, and each program is bounded by its limit on the physical memory. So where is the physical memory? The physical memory is inside the RAM. Okay, because the RAM size is not so big, so each program, each process that needs to be executed need to be stored inside here. However, the storage of the physical memory is not big, because it also needs to give its location to other programs, other processes as well. So because of that reason, only limited files or codes or programs are stored inside the physical memory. So where again is the physical memory? The physical memory is your RAM size, your RAM. Okay, each program takes less memory while running. More memory, more programs run at the same time. Okay, so that makes sense. So each program will take less memory location in the RAM size, in the RAM. Why? Because at least it can give opportunity to other programs to be inputted inside the memory as well. All right. So by doing so, the CPU utilization is much more better, and the throughput also is much more better. What is the throughput? The throughputs are all the outcomes that comes out from CPU utilization, the outcome, the output. Okay, so CPU utilization can be higher because there are other processes inside the physical memory, so it can run more processes at any given one time. And sometimes it's less input output needed because it does not need to there are certain input outputs from the particular process which are not needed at the moment. Okay, so by doing so we can only focus those programs which can be executed and needs to be executed at any one given time. All right, so next we go into a virtual memory. Okay, the idea of virtual memory is to separate logical memory from physical memory, whereby you separate the memory from CPU to RAM or from physical memory, RAM to hard disk. Okay, so a virtual memory is simply something like this. So you have your CPU here. Inside your CPU is actually the cache memory, and then you have the normal RAM here, and you have your you have your virtual memory here. Actually, the virtual memory is part of the RAM size. Okay, part of the RAM size, because the RAM is full. That's why it uses partially memory from the hard disk to become its virtual memory. All right. So basically, the CPU will come out with the logical memory, will come out, and will be translated into physical memory to locate the particular file of interest. So these blue lines here are what we say as the logical memory. Once the logical memory goes inside the RAM, it will be converted into physical memory. Okay, physical memory here. So the CPU sends a logical memory converted by the RAM to physical memory, and to locate the files inside your virtual memory or your hard disk, and then send it back to the CPU. Okay, so the CPU only knows logical memory. It does not know physical memory. So that is why inside paging, we do a calculation to convert logical memory into physical memory. Okay, so point number 2, logical address space can thereafter be much larger than physical address space. Okay, so logical address space is always larger than your physical address space. Okay, so the files that is needed by the CPU is sometimes, or it could be inside this location here. All right, which is the physical memory. Although it looks as if it is inside your hard disk, but actually what the operating system is doing is simply taking a part of the hard disk and converting this location into RAM, and this location is now known as the virtual memory. Okay, so virtual memory, logical view of how processes is stored in memory, right? So this is how the physical address is being stored, or how the files are being stored. So again, CPU comes up with a logical address, and this logical address is converted inside the memory management unit, which is located inside your RAM, and will be converted into physical address, and physical address to locate the files inside the memory. All right. So these files can be stored in a contiguous manner. Contiguous bermaksud bersebelahan. Okay, so these files can be broken. Kalau you are using paging, the program broken into several pages or frames. Okay, so program 2 is broken down into several pages, or what we say as frames. Okay, that is demand paging. Kalau demand segmentation, the program is now broken into several segments. Segment 2 is like several modules lah. Okay, several modules. So if the CPU needs, let's say in the demand segmentation, if the CPU needs a specific function or specific files, so it will now look into it will send a logical address to be converted into a physical to locate that particular file of interest. So the operating system does it in two manners. One is what we say as the demand paging. Another one is through demand segmentation. So basically, this is how demand paging and demand segmentation looks like. All right. So in demand paging, okay, the logical address, where is the logical address, is inside the CPU, will locate or will send a logical address to the MMU, or what we say as the memory management unit, which is located inside the RAM. All right, and inside the RAM there is something which is called a page table. What is the meaning of a page table? It shows the location of the physical address. It shows the location of the physical address. For example, let's say the CPU releases logical address 0. Okay, so it checks inside the page table, or page table is inside frame number 3, and it will locate this is the file, and it will send back the file here. Okay, and we also have another column here, which is valid. What does valid mean? Valid means this frame or this file is valid inside the physical memory, meaning to say it is available inside the physical memory. Okay, page number 2, frame number 5 is the location of this file here. Page 4, frame number 7 is the location of this. So it's a valid, okay, it's valid here. Invalid means there is no page or frame allocated inside it. All right, page 1 empty. Okay, it is empty, meaning there is no frame allocated for page 1. There is no frame allocated for page 3. There is no frames available or allocated to page 5 and 6. However, these files are invalid here, but valid inside the hard disk. What do I mean by that? It means that although these files are not here, but these files are actually inside your hard disk inside here. So later parts of the slides, we will understand how to bring these files over inside the frame and then update your page table. Okay, so I repeat myself. Invalid means the file is not, or the frames are not available inside the physical memory, but most probably it is valid inside the hard disk. It is available inside the hard disk. The file is there, but it's inside the hard disk. So we say it is invalid inside the page table, but valid inside the hard disk. Okay, it is invalid inside the page table, but it could be valid inside the hard disk here. All right, that is demand paging. Hard disk, sometimes in the slides, are called backing store. So when I say backing store, when you read backing store, it means the hard disk. In segmentation pula, okay, the files of the program are broken down into segments. So inside the logical address, this is all regarding one particular process. So each process is broken down into several segments. So this segment is for the main program. This segment is maybe for the program called square root, subroutine, stacks, and segment table. So all of these is related to one specific process or one specific program. Again, if the CPU needs a particular segment, for example, it will highlight to the segment table, which is also located inside the memory management unit, which is also inside the RAM, to locate the segment inside the particular, inside the physical memory. Example here, segment 0. It does not have frame number. It is inside limit 1000 base 1400, meaning to say the files that is needed by segment 0 is between 1400, which is this one, until 1000, the limit here. So 1400 plus 1000 becomes 2400. Let's say we are looking at segment 2. Segment 2 is inside, okay, segment 2 is inside 6300. Okay, 6300. Hold on. Okay, so 6300. Where is 6300? 6300. Okay, here 6300, and the limit is 400. Okay, 6300 plus 400 becomes 6700. Means this file of interest is inside this place. Segment 4 is inside 4700, 4700, and the size is 1000, so 5700. Meaning the file of interest in segment 4 is between 4700 and 5700 inside here. So this is demand paging and demand segmentation. All right. So in demand paging, okay, if the files are not inside the, here we are focusing on here, if the files are not inside the main memory or the physical memory, it is swiped out. That means whatever files which are here which needs to be swiped out, put it back inside the backing store and bring back new files here. If these programs are now completed, so dia akan dibawa keluar, masuk balik dalam hard disk dan masuk balik file yang baru. Okay, so this is what we say as a swiper. Swipe in and out. Out means the files are completed, the program is done, so you swipe it back into your backing store, into your hard disk, and you swipe in back the new files that you need here. Okay, so we are going to look at the invalid reference, the I and the V. Invalid but valid as well. All right, so we have, so could bring entire process into the memory at load time. That means the program could bring everything inside here, or bring a page into memory only when it's needed. Dia boleh bawa semua atau dia boleh bawa satu saja from the backing store, from the hard disk into the main memory or the physical memory. Okay, so in swapping, pages guess which page will be used before swapping out again. Meaning, when the pages are brought from the hard disk into the physical memory, so dia akan main teka je. Okay, there is no specific rule. Okay, which file to bring in. Okay, so the files are brought in inside the physical memory, and then they can update the page table to show that, okay, now these pages are available inside the physical memory. And then we have a valid invalid bit macam saya tunjuk tadi. So valid invalid bit meaning to say the frames or the page number is valid and is inside the hard disk. Kalau dia invalid, it shows two conditions. It means the page is, the frame is empty and the file of interest is inside the backing store or hard disk. Okay, so let us look at this example again. Page 1, frame tak ada apa-apa, is invalid. What does invalid mean? Invalid means the frame is not available inside physical memory, but the frame might be available inside your hard disk here. Page 2, frame 6, valid means the frame is valid and the file of interest is inside physical memory, location number 6. Page 5, okay, page 5, frame 9, this frame 9 is valid, meaning to say the file of interest in page 5, frame 9 is valid and is inside the physical memory over here. So these files B, D, E, G, H are valid inside the hard disk but invalid inside the page table. Example. Okay, example. Page 7. It is invalid sebab it is not inside the physical memory, but it could be valid inside the hard disk here. Okay, it's valid inside here. Dia ada kat sini, but it's not inside here. So now to bring this inside here, the swapper, or dia akan swap masuk ke dalam ini and dia akan update ke dalam ini. If the files are not available, for example, let's say frame number 4, or sorry, page number 4 wants to access this. So it will check here, okay, page number 4, and it's invalid. If it's invalid, then the operating system will do a special task, which is it will do a special signal, which is called the page fault. The page fault means the files are not available inside the physical memory. Okay, I repeat myself. Page fault means the files are not available in the physical memory, but the files are available inside the backing store on the hard disk. Okay, so if the logical file tries to access a physical file which is not available inside the physical memory, then it will create a page fault. A page fault means the file of interest is invalid inside the page table, but it is valid inside the backing store or hard disk. So when this happens, the operating system will get the files from the backing store or hard disk, put it inside your physical memory, and then update the location of the page table so that the logical file or the CPU can access this particular file of interest. Okay, so if there is a reference to a page, the first reference will create a page fault. A page fault meaning the frames or pages are not available inside the physical memory. Okay, now this is how it works like. So this is the logical. First dia akan check dengan page table. Okay, kalau invalid, so dia signal kat OS. OS akan look for the file inside the hard disk. Oh, ada kat sini rupanya. Bawa file tu masuk balik dalam, dia akan cari frame mana yang kosong, masuk balik dalam physical memory, and then dia akan update balik table ni and put V here and say now the page of interest is inside this particular frame. So this is quite simple. First, the logical will try to access the page table. Can you give me 1 minute? I have a phone call to attend. Okay, can you just give me 1 minute? Okay, let us continue. All right, so let's go back to page 4 here. Okay, so if the if the CPU requests a particular file of interest, first it will check with the page table. Okay, ada lah kat sini. Okay, ada. Kalau tak ada, then it will set a trap or interrupt to your operating system. So operating system will be notified saying that, okay, the file tak ada, it's not inside here. We need to get the file from the backing store or the hard disk. Alright, so the files are okay, the files are here. Now bring it back inside the and put it back inside the physical memory, and then update balik page table and put a V sign here. So V means valid lah. Okay. Now the question arises. From here, kat mana dia nak letak ni? Can it put here, 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 or here? So obviously, dia akan berbuah dekat mana-mana location yang kosong. But there is always a question, dia nak letak kat location atas ke, bawah ke, tengah ke, okay, anywhere. So there is an algorithm that the operating system will follow in order to put in order to locate or to put down in which location should the file go to. Okay, so should it be put here, 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 or here? Okay, so there is an algorithm that the operating system will follow. Or let's say if there is all full here, semua penuh dekat sini. So what the operating system will do is it will choose which page or which frame is not used anymore. Yang mana dah tak guna, yang mana lama lagi nak guna, yang mana baru guna, yang mana takkan guna dah, so dia akan keluarkan. Okay, so there are few conditions kat mana dia nak letak. Satu, dia boleh letak dekat frame yang lama lagi nak pakai. Lama lagi nak pakai baru, okay. Or maybe they will put it at a frame yang which is not going to be utilized anymore. Or maybe they will put it at the last possible place. Okay, so there are few options or few algorithms that need to be followed. All right, so that is called what we say as a page replacement. Okay, so a page replacement is to prevent over allocation of memory by modifying page fault. Maksud dia over allocation, that means you put more than what is required. Walaupun the file is not being utilized, you dah letak siap-siap dah. Or maybe the files are not being used anymore, but the operating system still keeps it. So that is what it means by over allocation. Or maybe you can use the modify bit to reduce overhead page transfer. Only modified pages are written into the disk. Meaning, if there is a file here and the file has an update, ada file baru, then you put in a new allocation. Kalau the file is the same, okay, contents dia sama, boleh dikeluarkan balik. Alright, so how do we do it? So in order for to locate the frames, okay, the operating system first will check which frame is free lah. Kalau tak ada frame yang free, dia akan gunakan page replacement technique untuk choose a victim frame. A victim frame meaning frame mana yang kosong atau frame mana yang takkan digunakan ke, akan lama lagi nak guna ke, or any other thing, dia akan pilih randomly, masukkan saja. Okay, so it's like this. Alright, so invalid. Alright, so first it comes to logical masuk. Invalid, dia akan choose, okay, kat mana location. So dia akan pilih je, okay, I will choose this location, so start masuk kat sini. So file ini akan dibawa keluar. Bawa keluar kat sini. But why do you choose this? Ada algoritmnya. Kenapa kita pilih yang ini? Why do we choose this? Because maybe there are other locations semua dah penuh dah. But the operating system chooses this because mungkin file ni dah akan belum pakai lagi. Ataupun lama lagi nak pakai. Okay? Or maybe some other issues as well. So it will choose a victim frame. Alright. So these are some examples of how the operating system chooses a victim frame. Dia akan ada algorithm which is called the first algorithm is called the first in first out algorithm. Okay, so let us look at this example. So these numbers here represent the page number. Okay, the page number. Okay, page numbers. Okay, so these are all, okay, these are all the frames available inside the physical memory. So you boleh bayangkan inside the physical memory, which is this one here, there are only 3 locations. 3 location. Okay, there are 3 locations. Alright. So these are the files from the hard disk yang akan masuk ke dalam physical memory or your RAM lah. Okay. So 7, file number 7 masuk dekat first location. File number 0 masuk dekat second. File number 1 masuk dekat sini. Alright. Now, file number 2. File number 2 nak masuk kat mana? Because 7 semua dah ada. So in the first in first out algorithm, dia akan masuk dekat nombor 7. Because 7 was the first one. Okay, masuk sini. Next, kosong. Oh, kosong memang dah ada, so dia replace saja kosong ni. Okay, so that's why there's nothing here. Okay, there's nothing here because 0 is already here. Alright, 0 is already here. So there's nothing here. Next, dia akan masuk 3 pula. 3 masuk dekat kosong sebab that was the last input. Alright. Next, dia akan masuk 0. Okay, 0 dekat number 1 here. 4 pula. 4 masuk dekat 2 because that was the first in balik. So dia ulang balik lah. Dia ulang balik. 4. 3, 0. 2 masuk dekat number 2 here. 3 masuk dekat 3 here. 0 naik balik. And then 3 dah ada dah. 2 oh dah ada dah. 1 masuk dekat 2 because that was the last place. Okay, last place tadi. And then 3, 1. Okay. And then 2 masuk dekat 2 here. 0 oh dah ada. 1 dah ada. 7 masuk dekat atas. Because 2 was the last one here. Okay, 7. 0 oh 0 masuk dekat 1. And 1 masuk dekat 2 here. Okay. So each time the file goes inside the location, we call it as page fault. So jumlah page fault ialah 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 times. So 15 page faults yang dijumpai if we are using first in first out algorithm technique. Okay, first in first out technique. Okay. Then there is also another possibility, kalau why not kita increasekan, okay, why not kita tambah frame. Sekarang ni ada 3 frame saja kan. So why not kita tambah 4 frame. Meaning 7, 0, 1, 2 kat bawah. Macam tu. Alright. But dalam algorithm first in first out, if you tambah more frames kat sini, then you will lead to a problem called Bilady's anomaly. Bilady's anomaly kata, even if you tambah the number of frames kat sini, okay, your page fault will also increase. Okay, your page fault will also increase. Okay, because each frame needs to be in a specific location at a specific time only. Okay, all right. So that's Bilady's anomaly. All right. Now let's look at optimal algorithm. Yang tadi itu is first in, first out. Optimal algorithm, example yang sama. Okay. Replace page that will not be used for the longest period of time. Maksud dia, lama lagi nak guna. Okay, that means we have to look ahead. That's why I drew an arrow here. You have to look ahead. That means file ni akan digunakan lambat lagi, so we can take it out first. Lambat lagi dia nak guna, so we can take it out first. Okay, start with 7, 0, 1. Okay, 2. 2 nak masuk dekat 7 ke 0 ke 1. Okay, so we look on the right hand side. After 2 is 0. Oh, lepas ni dia nak pakai 0. So that means 2 cannot replace 0. Okay. Lepas tu dia nak pakai 3, tak ada kaitan. Lepas tu lama lagi dia nak pakai 1. Oh, but 7 is at the end of it. Lambat lagi. At the end baru pakai 7. Okay. So 2 can replace number 7. Alright. Next 0. Oh, 0 dah ada dah. 3. Okay, 3. Should it go here? Should it go 0 or should it go 1? So dia check ke kanan. Lepas 3 is 0. Oh, cannot. tak boleh masuk kosong sebab lepas tu dia nak pakai. Oh, 2 tak boleh juga. Okay, and 1 lama lagi. So that's why number 3 dia akan replace kat number 1 because number 1 is being utilized tapi lambat lagi. Alright, so 0 tak ada apa-apa. Alright, 4 nak masuk kat 2 or replace 0 or replace 3. Alright, so check 4 lepas tu 2 and 3. Lepas 4 ni ada 2 and 3. So 2 and 3 tak boleh pakai, kosong yang hujung sekali. So 4 will replace 0 here. 2, 3, 0. Okay, 2 ada, 3 ada. Okay, now 0. 0 should it go into 2, 4 or 3? Check. Ke depan. Lepas 0 is 3 and 2. So 3 and 2 kita tak boleh kacau. 4 boleh. Sebab 4 tak akan dipakai dah. Alright, so masukkan 0 kat sini. 3, 2, 1. Okay, 2 and 3 dah ada. 1. 1 should it be going to 2, 0 or 3? Okay, check. Lepas 1 is 2 or tak boleh. Lepas 2 is 0 or tak boleh juga. 3 takkan dipakai dah. So 1 goes inside 3, the third location here. Alright. Next you have 2. Okay. Next you have 0. Okay. Next you have 1. Okay. 7. 7 goes into 2, 0 or 1. 7 lepas 7 is 0 tak boleh. Lepas 0 is 1 tak boleh. Okay, 2 because 2 is not going to be utilized anymore. So we put number 7 at the top here. So number of page 4 ialah 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Okay, so we use number 9. Okay, so optimal gives you number 9. That means the number of page 4 by using the optimal solution, the optimal algorithm is 9. Next, we use least recently used. That means we are looking at the pages that has not been used in the most amount of time. We look behind. Okay. 7, 0, 1. Okay. Next, kita nak masuk 2. So, either 2 masuk dekat 7, either 2 masuk dekat 0, either 2 masuk dekat 1. So 2 akan masuk dekat, we have to look behind. Before 2 is 0 and 1, so we do not replace 0 and 1 because that it's still it can be still utilized. But 7 was yang pertama tadi. That means the last one we use, or the last hujung sekali is number 7. So we replace with number 7. Okay. So next 0, okay. Next 3, okay. Now 3. Should it go into 2, 0 or 1? Okay, look behind. 0 and 2 or 0 and 2 kat sini tak boleh kacau. 1 is the one before. So 3 goes into 1. Alright, now 0. Okay, 0 dah ada. 4. Look behind. 4 cannot go into 0. So sebelum tu 0. Cannot go into 3. But 2 is the last one here. So 4 takes in 2 here. And then 2. Okay, 2. 4 dengan 0 tak boleh. 4 dengan 0 tak boleh. 3 boleh. Sebab 3 hujung sekali. Masuk dekat 3. Okay, masuk. Sorry. 2 masuk dekat 3 here. Okay. Now number 3 pula. Number 3, either you go 4 or 0 or 2. Okay, check belakang. 2, 4, 0. So you cannot replace 2. You cannot replace 4. But you can replace 0. So that's why 3 is here. Okay. So now 0. 0, you look behind. 3, 2, 4. 3, 2, 4. Okay, semua dah ada. But 4 was the last one used here. Hujung sekali. So 0 goes here. 3 ada, 2 ada, 1. Where does 1 go? Tengok ke bawah. 2, 3, 0. Okay, 0 was the last one. So it replaces number 0 here. 2 and 0. Okay, 2 ada, 0. Okay, now 0, 2, 1, 2. Okay, tak boleh juga. Oh, 3 is the last one here. Alright, so 3. So 0 here. So 1 and 2 here. Next 1. Okay, dah ada. 7. You want to go behind. 1 tak boleh. 0 tak boleh. 2 boleh. So 2 yang paling jauh kat sini. So goes into number 2 and 0 and 1 here. So number of page 4 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. Better than first in, first out, but worse than optimal. Okay. So the best one is always optimal. The second one is least recently used. And the final one is first in, first out. Okay, do you have any questions on this? Ni soalan ini penting ni, nak kena tanya ni. Any questions on this?
No, sir.
All right, next we go into thrashing. Okay, so thrashing means if the process does not have enough pages. Maksud dia from the physical nak bawa masuk, from the backing store nak masuk to physical, it does not have enough pages, then the page fault rate is very high. Why is the page fault very high? Because it has to, when the page fault happens, page fault means the file is not inside the physical, but the file is inside your hard disk. Okay, so page fault happens, the file of interest tak ada dalam your physical, but it's inside your hard disk. So operating system needs to go and get from the hard disk, masuk balik dalam physical. So the longer it does this, it is called, the process called thrashing. So when you call thrashing, CPU cannot do anything because CPU is still waiting. So CPU utilization is very, very low. Okay, because it's not doing anything, it cannot do anything. So file tu tak ada lagi. Okay, so thrashing means a process is being swapping in and out. So what it needs to do is, how to prevent swapping is the operating system needs to work fast and needs to choose the best algorithm to suit the process so that thrashing is low. Bila thrashing is low, at least CPU can do something. Because if the thrashing is high, asyik buat keluarkan file, CPU is not doing anything. Simple example, if you're downloading something and if the file is very big, sometimes your PC will hang. Sometimes your PC won't do anything because it's working too much on a certain thing, which is downloading something, is doing this saja, but it's not doing what it's supposed to do, which is CPU utilization. Okay, so that is what thrashing means. Thrashing means is doing too much of page fault and your CPU utilization is very low. Okay, so when you have your CPU utilization very low, then your degree of multi-programming is also very low. What is multi-programming? The ability of the CPU to run multiple programs. Okay, so the CPU cannot run multiple programs because thrashing is very high. What is thrashing? Thrashing is the process of bringing the files from your backing store masuk balik dalam physical, So it keeps doing this. So your CPU utilization is very low. If your CPU utilization is very low, then your degree of multi-programming is also very low. Okay, so that is all for chapter 9. Okay, that is all for chapter 9. So what you need to understand in chapter 9 is the paging. You need to understand the concept of demand segmentation, and you need to understand how the page replacement technique works. So we have first in, first out. We have optimal, and we have least recently used. You have to know how to do these diagrams. You have to know how the algorithm works, and from that you have covered chapter 9. Okay, so we're going to stop here for today. Before we stop, do you have any questions to ask me? Ada soalan nak tanya saya? Alright. So you, if you don't understand, you can just look at the videos. I will upload this in my most probably YouTube, and then you can look at it and understand in your own time. If you don't understand, please contact me as well. All right. Thank you so much for attending my class today. Do not forget to sign your attendance, and I'll see you in the next class. Thank you so much. You have a good day. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Waalaikumsalam.
Thank you.